Hello everyone and welcome to this week's OpenGL 3D game tutorial, and this week we're going to be texturing and animating our particles. So last time we created some simple particle systems with some plain white quads, but this week we're going to be applying textures to these quads to make the particles look a little bit more interesting. We're not just going to be texturing the particles with a single texture though, we're going to be using texture atlases like this so that the textures on the particles can be animated and change over time. The way that we're going to get this to work is that every frame for each particle we're going to work out which stage of the texture it should use based on how long it's been alive for. We'll then do some very similar stuff to what we did way back in tutorial 23, which was the texture atlas tutorial, and we'll use the concepts that we implemented back then to get the texture coordinates for the current texture stage and the next texture stage. We can then fade between the current stage and the next stage based on how close the particle is to reaching the next stage, creating some smooth progressions between these different texture stages. So let's jump into the code now, and we're going to start off by creating a new class, and this is going to be the class for the particle texture, which represents one of those texture atlases that could be used to animate our particles. So this is going to need an int, which is the ID of the loaded texture, and it's also going to need to know the number of rows that are in the texture atlas. I'm then just going to generate a constructor, a very simple constructor here, and we're also going to need to generate some getters so that we can get these values from other classes. Let's now go into the particle class because we need to give each particle its own texture. So we're going to create a private particle texture, and we're going to make the constructor take in a texture, and of course we need to set the texture here, and then we also need a getter method. So I'm just going to generate a getter method for the texture here. Now I'm going to go into the particle system class, and each particle system also needs its own particle texture, and then every particle that this system creates will have that texture. So we also need to take in the texture in the constructor here and set the texture, and then down in the emit particle method, whenever we create a new particle, it needs to use the particle texture. We're now going to go into the particle master class, and we're going to do something similar to what we did with entities and textures, and that is to have one list of particles for every texture that's being used, and we're going to associate each particle texture with the list of particles that use that texture in a hash map here. So we need to change the list of particles to a hash map which has multiple lists of particles, each one associated with the particle texture that all of the particles in that list use. So we now need to update a few of the methods in here. So let's start with the add particle method. This now needs to get the relevant list to add the particle to, and to get the relevant list we're going to do particles.get, and then we put in the particles texture, and that will return the list of particles that use that texture. But if that list doesn't exist, for example if this was the first particle to get added, then the list wouldn't have been created yet. So if the list doesn't exist, we need to create the list, create a new array list, and then we're going to add that array list into the hash map by calling particles.put. The key is the particle texture and the value is the list. And now that we know that that list exists, we can add the particle to that list, and that will add the particle into the hash map. We're now going to go into the update method here, and we're going to update this. So for now, just move all of the previous code down a bit, and we're going to create a new iterator to iterate through all the entries of the hash maps. That's basically going to iterate through each list of particles that the hash map has in it. And to get this iterator, we can call particles.entrySet.iterator, which returns an iterator for all the entries in the hash map, and each entry is a particle texture list of particles pair. So we'll start iterating through all of the entries in the hash map, and we're going to get each list of particles by calling mapIterator.next, which will return the next entry, and then we're going to get the list associated with that entry. And then once we've got the list, we're going to do all this code that we did previously. So just cut and then paste all of that previous code here. We need to change particles to list now because that's what the name of the particle list is called. And also one last thing, when we remove a particle from the list, we now need to check if the list is empty, because if the list is empty, we can actually remove it from the hash map by calling map iterator.remove. So this method just iterates through all of the lists of particles, and then for each list of particles it iterates through all of the particles and it updates each of the particles, removing any if necessary. Finally, if we look down here at the render particles method, the render method in the particle renderer is still obviously taking in a list of particles, so we need to change that so that it takes in this hash map of the multiple lists of particles and their corresponding particle textures. We're now going to create an outer for loop here, which is going to loop through all of the different particle textures that are being used, and this for loop needs to contain completely this other for loop, so make sure you put that second bracket in the correct place. And what this is going to do, it's going to loop through all of the textures. For each texture it's going to bind the texture and then render all of the particles that use that texture. And to bind the texture we need to first activate the texture unit that we want to bind the texture to. So we're going to activate texture unit 0 here by calling GL active texture GL texture 0, and then we're going to bind the texture to texture unit 0 by calling GL bind texture, and then putting in GL texture 2D because it's a 2D texture, and we then put in the texture's ID. We now need to go into the particle vertex shader and do a little bit of work in here. So we need to output some texture coordinates so that the texture can be sampled in the fragment shader, and we're going to calculate these texture coordinates in the vertex shader based on the vertex position, and we did a very similar thing to this in the GUI tutorials. So what we're going to do here is we're just going to add 0.5 to both the X and Y position, and we're then going to flip the Y texture coordinates by doing textureChords.y equals 1 minus textureChords.y. So let's now move into the particle fragment shader, and in the fragment shader we of course need to take in the 2D texture coordinates and make sure to spell that variable the same as you spelled the output variable in the vertex shader. And we also need a sampler 2D for the particle texture. So we can now set the output color of the fragment by sampling the particle texture at the texture coordinates. And that is now all the code that we need to give our particles a simple texture. We haven't implemented the animated textures yet, but let's just test this out for now. So create a new particle texture in your main game loop using whatever texture you want to use for your particles. So I'm just going to load up a texture that I have in my res folder called particle star. And the second parameter is the number of rows in the atlas, and obviously we're not using particle atlases yet, so that's just one row. And give that texture to your particle system and go ahead and run it, and you should hopefully now have some nice textured particles. So this all looks good so far, but there's actually a little bit of a problem with the depth testing here. Some particles that should be hidden behind other particles are shown in the foreground, whereas other particles that have nothing in front of them seem to get hidden behind others. You can see here that it actually always renders the newest particles in front, even if they should be hidden behind hundreds of other particles. This is because we turned off depth writing last week, which means that particles aren't written to the depth buffer, and so they simply appear in the order that they're rendered, with the last particles to be rendered always appearing in front of all the other particles. Enabling depth writing for the particles doesn't really help though, and it in fact makes the situation a bit worse. You can see here that the quads of the front particles are now hiding the particles behind them, even though most of the quads should actually be transparent. This occurs when a particle is rendered behind another particle, but after that other particle has already been rendered. When the first particle is rendered, the whole quad is written to the depth buffer, regardless of whether the texture it uses contains transparency. If another particle is then rendered behind that first particle, the depth test will do its job and it will make sure that none of the particle's pixels that are behind the other quad are rendered. So writing the particles to the depth buffer is really not going to be much use to us because it doesn't take the transparency into account, and that's why we disabled depth writing for the particles last week. So it's now just all down to the order that the particles are rendered in. Particles rendered first will be rendered at the back, and particles rendered later will be rendered in front. So in order for this to look correct on the screen, we're going to need to order the lists of particles before they get rendered to make sure that the particles furthest away from the camera get rendered first, and particles nearest to the camera get rendered last. We're not going to do that just yet though. What we're going to do now is to try out a different type of blending, which is order independent, so it makes no difference which particles are rendered in front or behind. Up until now we've just been using alpha blending, but what we're going to do now is we're going to use something called additive blending. When a particle is rendered to the scene with additive blending enabled, it simply adds the particle's colour with whatever colour is behind it. So it doesn't matter which particle is rendered on top here, because no matter what order you add the colours together, you're always going to get the same result. So if we go into the particle renderer class, we can change the blend function to use additive blending, and we can do that by simply changing this second parameter here to just GL1. And if you go ahead and render that, you can see that the stars are now a lot more glowy, and this is because they're using additive blending, which is great for effects like fire or magic effects, but perhaps not so good for things like smoke or objects that you want to look solid, like falling leaves or bits of rock flying off when you hit something. We're now going to start working on animating the textures by using a texture atlas like this. For every particle, every frame, we need to find out which stage of the texture it should use based on how long it's been alive for, and we then need to be able to change the particle's texture coordinates to use this part of the texture. If you look back to the texture atlas stuff that we did before in tutorial 23, you'll see that we need two things to calculate the new texture coordinates. We need the number of rows in the texture atlas, which is a value that we already have in the particle texture class, and we also need to know the x and y offset for the texture coordinates, which indicate where on the texture atlas the top left corner of the part that we want to use is. And seeing as we also need to know the texture coordinates of the next stage, we'll also need a second xy offset. And finally, we need a blend value indicating how much the current texture stage should be faded into the next texture stage. So let's start implementing some of this stuff into the code. So in the particle class, each particle, as I just mentioned, needs to have two offsets, one for the current stage in the texture atlas and one for the next stage in the texture atlas. And both of these texture offsets are of course 2D coordinates. And we also need a float value, which is the blend factor. I'm now just going to generate some new getters for these values. So get blend, get text offset 1 and get text offset 2. And we're now going to create a private method which is going to update these texture offsets and the blend value every single frame. So down at the bottom here we can create a new private method called update texture chord info, and we're going to call this from the update method so that it gets called every frame. The first thing that we're going to do in this method is to calculate a value between 0 and 1, which indicates how far into its life the particle is. So a value of 0 would be that the particle's just started its life, and a value of 1 would mean that its life is just ending. We're also going to calculate an int, which is the number of stages in the particle texture atlas, and we can calculate this very easily by squaring the number of rows in the texture atlas. We now want to find out how far along the stages this particle should be, and we can calculate that by multiplying the life factor, which is the number between 0 and 1, by the stage count, which is the number of stages in the atlas. So by doing that, we would get a number indicating how far along the atlas that particle should be, with the number before the decimal point indicating the index of the current stage, and the fractional part of the number is a number between 0 and 1, indicating how close to the next stage the particle is, and we'll be using this fractional part as the blend factor. So let's now do that in the code. So the index for the current stage in the texture atlas can be calculated by simply flooring the atlas progression value, and we're going to need to cast that to an int. And we also want to calculate the index for the next stage in the texture atlas, which we can do by simply adding 1 to the index of the current stage, but only if the current stage isn't the last stage in the texture atlas, because if we're already in the last stage of the texture atlas, then there is no next stage, so we can just set the next index to the current index because there is no next index. We also need to calculate the blend factor value, which, as I mentioned earlier, is just the fractional part of the atlas progression value. So let's calculate that. And now we've got the index of the current stage and the index of the next stage, but we need to convert those indices into offsets, into texture offsets for both the current stage and the next stage. So I'm going to create a method that can do that, that converts an index into a texture offset. And to do that, we're going to use a calculation that we used back in the Texture Atlas tutorial. And the first thing we do is we find out the column and the row of the stage in the Texture Atlas that the index is referring to. And then based on those column and row values, we can very easily calculate the X and Y texture offset. And we're going to need to cast both of these values to a float. So the X offset is column divided by the number of rows, and the Y offset is the row divided by the number of rows, and again we need to cast that to a float. So we're going to call this setTextureOffset method for both of the stages. So to calculate texture offset 1, we're going to put in the index of the current stage, and to calculate the texture offset 2, the offset for the next stage, we're going to put in the index for the next stage. So that's the particle class done, and we can now move into the vertex shader. This now needs to output two texture coordinates 1 and 2, one for the current stage and one for the next stage. And we also need to output the blend factor, how much these two stages should be blended together. We're also going to have a few uniform variables, so 2 uniforms for the 2 texture offsets. And we also have a final vec2 uniform, which is going to have 2 more floats of information, one of which is the number of rows in the atlas, and the other is going to be the blend factor. We need to add a vec2 here because the texture chords variable no longer exists, and we now need to convert these texture coordinates into the 2 new texture coordinates that we need for the 2 different stages. And again, this is something we did back in the Texture Atlas tutorial. So we're just going to use the texture offsets to convert the original texture coordinates into the texture coordinates for the 2 stages here. So make sure you get the text offset 1 creating the texture chords 1, and the text offset 2 creating the texture chords 2, and the blend factor, as I mentioned, is just the Y component in the text chord info. So let's move into the fragment shader. The fragment shader now needs to take in these texture coordinates 1, texture coordinates 2, and in float blend. And we're now going to sample the texture atlas at the 2 different stages. So color 1 is going to be the color in the current stage by sampling the particle texture atlas at texture chords 1, and we're going to have color 2 as the color in the next texture atlas stage. And then the output color is going to be a mixture of these 2 colors, and to mix these 2 colors together we're going to use the blend factor. We now need to go into the particle shader class and do the usual thing for the uniform variables, and I've sped this footage up a whole load because I'm sure you all know how to do this by now. So we need an int to hold the location of each of those 3 new uniform variables. We're then going to get the location of those uniforms, making sure to spell the uniform names correctly here. And we of course need a method which will allow us to load up values to those uniforms. So this method is going to take in 2 offsets, the number of rows and the blend factor, and it just has to load up those offsets to the relevant uniforms. And finally we have to load up one more 2D vector to the text chord info uniform, and this 2D vector is made up of the number of rows in the X component and the blend factor in the Y component. Finally, in the particle renderer class, for each particle we need to load up those offset values. So in the inner for loop, we're going to call that new method in the shader class to load up the text offset 1, text offset 2, the number of rows in the texture atlas, and also the blend factor for this particle. So we're pretty much done now. All we need to do is in the main game loop we need to choose a texture which actually is a texture atlas, and I've got one in my res folder called particle atlas, which you can download from the description, and that has 4 rows in it, so the second parameter has to be 4. And as you can see, if I run that, the particles now have an animated texture which changes over the particle's life. Let's now sort out the problem with alpha blending. So let's go back into the particle renderer class and set the blend function back to using alpha blending. If we then go ahead and run this, you'll probably be able to see the ordering problem again, with the newest particles always appearing in front of all the other particles. and that's because the newest particles are the last particles to get added to the list, and so are the last particles to get rendered, and so get rendered on top of all the previously rendered particles, even if they should actually be hidden behind them. As I said earlier, the way to sort this out is to order the particles by distance from the camera, so the first thing we need to do here is to calculate a distance from the camera for each particle. So in the particle class, each particle is now going to have a distance value which will represent the distance of the particle from the camera, or actually the distance squared. We're then going to generate a getter method for this distance, and then in the update method we're going to update the distance value every frame. So this needs to take in the camera now so that we can use it to calculate the distance from the camera. And to calculate the distance value, we're first going to find the vector from the particle to the camera, which we can get by subtracting the particle's position from the camera's position, and then we can find the length squared of that vector, and we're using the length squared here because it's more efficient than calculating the length, and it does exactly the same job. In the particle master class, we also need to have the update method take in the camera so that we can give it to the update methods which we call on the particles. And in the main game loop, when we call particlemaster.update, we need to give it the camera. Now that we've got a distance value for each particle, we need to decide on a sorting algorithm to sort the lists of particles. One important thing to remember is that the particles don't move or change position that much in a single frame. So if the particle list was sorted last frame, then it's pretty much already going to be sorted this frame, with perhaps just a few particles out of place and a few new particles to sort into the list. So we don't really need an algorithm that's really fast at sorting completely random and jumbled up lists. We need an algorithm that's good at sorting lists which are pretty much already sorted. For this, I've chosen to use an insertion sort, and you can download my simple implementation of this from the description of this video, and then just put it into your particles package in your project source folder, and then in Eclipse you can refresh your project to be able to see the code. If you want to use a different sorting algorithm, or if you've got a more efficient way of implementing the insertion sort, then by all means use that instead, but this simple insertion sort should work fine for now. If you'd like to learn more about the insertion sort and how it works, then you can check out the video that I've linked below in the description, or just do a Google search for it and you'll find loads of explanations. And all we need to do with this in the code is in the particle master class in the update method for every list of particles, so just outside that inner while loop, make sure you get this in the right position, we're going to call the insertion sort for each particle list. So if we go ahead and run that, all the particles should now be sorted and rendered in the correct order, and as you can see we have alpha blending enabled and we no longer have that depth problem. So we've basically got everything working now, and you can use these particle systems to create any number of different effects, but there are still a few things that you could improve in this system. Firstly, you might want to be able to make use of both additive and alpha blending, so you could add a boolean into the particle texture class and then decide which blending function to use before rendering. That would allow you to have nice glowing magical effects, as well as alpha blended effects such as smoke and falling leaves. There's also still a bit of a problem with ordering, because although we ordered the individual particle lists, the lists themselves aren't ordered, and so one set of particles may be rendered in front of another set of particles when it shouldn't be. One way of fixing this would be to sort all of the particles in the scene in one big sorted list, but then we might have to bind and unbind textures after rendering each particle, which would be rather inefficient. Another solution would be to sort the lists themselves to choose which lists of particles should get rendered before others, but that still wouldn't solve a problem like this, where two particle systems using the same texture atlas are in front and behind some other particles using a different texture. A good way of solving this problem would be to make use of texture atlases again and put multiple particle atlases into one big texture atlas. That way, all of these particle systems could use the same texture, and so would all be in the same list, and so therefore would all be ordered correctly before rendering. So you can have a go at implementing something like that yourselves by using the texture atlas tutorial and this tutorial, but I'll provide you with a working example of it anyway next time if you have any difficulties. So for this week, that is it. Next time we're going to be finishing off particle effects by optimizing the system as much as we can, which we'll mainly be doing by implementing instanced rendering. If you want to help support the series, there's a link to my Patreon page in the description below, and you can get in touch with me via any of my social media pages. But yeah, thank you guys very much for watching this video. Do subscribe if you haven't already. Have a fantastic week, and I will see you all next time.